Hello, Calc 3 friends. This is a video, this is Ben Marlin, and this is a video talking about the limit comparison test. The limit comparison test is probably the most intuitive of the tests that we've used so far, but the actual mechanics of it are sometimes a little bit tricky. All right, let me show you the actual thing that we have to write down, okay? So you'll have a more complete statement of the limit comparison test in your textbook, but the basic statement I want to look at here is kind of stripped down. This, you've got to be talking about two series. Now, I've written down summation n equals 1 to infinity of an and summation n equals 1 to infinity of bn. The beginning point of that doesn't matter. It could be starting at n equals 0, n equals 2, or whatever. But it is important that we have two positive sequences that we're working with. And we want to be able to divide the terms, not the partial sums, the terms, and to be able to have something we can actually take the limit of. So this limit here that I've just labeled L, it can be 0 or it can be infinity. Those are fine. But the very most basic form of the limit comparison test is if the L is neither 0 nor infinity, it's just some bounded number, then either both series converge or both series diverge. Okay. If you're thinking of this in a more intuitive sense and you know a little bit about growth rates, when that limit turns out to be positive and finite, that means that the two series essentially have the same growth rate, okay? Now, the confusing part, at least for me, the confusing parts, and I realized, you know, the confusing part is when we have to deal with the exceptional cases. It used to be that calculus textbooks just didn't bother with these exceptional cases, but now this textbook does. If you get a limit of 0 out of that, that means intuitively the growth rate of the bottom had to be more than the growth rate of the top. So then you can say if L equals 0 and you know something else. Let's say that the summation of the a sub n's, that's the ones on top, if that diverged, okay? So the ones on top diverge, but have a smaller growth rate than the ones on the bottom. Then the ones on the bottom have to diverge as well, okay? Because something that diverged had a smaller growth rate than the thing that was being divided by. So the thing it was dividing by had to have diverged as well. But if your L is 0 and you know that the ones you're dividing by converge, then the ones that are being divided have to have a smaller growth rate, and that means that they have to converge as well. Converges. Okay. So that means there's two different ways to play with the test. if you've got an L equals 0. If you know one of them converges or the other converges, it might tell you something about the other. But if I got L equals 0 and the ones I was dividing by, the BNs, if those diverged instead of converged, it wouldn't tell me anything. And if the ones that were being divided by, if those converged, it wouldn't tell me anything about the ones that were being divided. So it is a little hard to keep track of, but I usually just use it in the first case with a positive and finite version. But if you're using something from the textbook, then you have some extra cases. And I don't think that your text actually writes out all of these implications of what they've got. Summation of the BNs diverges. The summation of the ANs have to diverge as well if you were getting infinity out of it. And if you got infinity and the summation of the ANs converge, the summation of the BNs converge. Okay, so it's always on these some sort of conclusion about the growth rates being similar, not opposite. Okay, so how do you use these? The place that you'll use them the most often is when you have to test something and you, first of all, don't know the expression for the sequence of partial sums. If you know that, it's always easy. So you're definitely just dealing with terms. But you're using this most often when you've got something that looks like it ought to be a p-series, but it's not. Okay, so something where you can see a polynomial on top and a polynomial on bottom, and you can tell what the difference is in those powers. You are going to, in your head, say, "Oh, that's a p-series with p equals blah," and it's not a p-series, but it acts just like one, and the limit comparison test lets us say that. Okay, so a quick example that works out along those lines would be if we were doing a summation something like this, maybe n equals 1 to infinity, and we've got on top the n plus 1, and on bottom maybe it's 2n cubed plus n. Okay, so trying to make it not too complicated. And you might get instructions like determine convergence. Now that does not beg the question. It doesn't tell you whether it converges or not. It really means determine whether it converges or diverges, but it's determine the nature of the series. So taking a look at that, your terms, you immediately say, aha, top is first degree, bottom is third degree. This is like a p-series with p equal to 2. So I'm going to say this is like summation n equals 1 to infinity, 1 over n squared, which converges by p-series. Okay, and then I'm going to take my limit as n goes to infinity. Now in this particular case, it doesn't matter which one you put where, but I'm going to put the n plus 1 over 2n cubed plus n on top, and on the bottom I'm going to put the 1 over n squared. And you're going to simplify your fraction there and have your top be n cubed plus n squared, and your bottom be this 2n cubed plus n. If you are super OCD and you want to go through all the stuff of doing L'Hopital's rule, you can totally do that. Or you could say highest powered terms on top and bottom are the power of 3. I just need to divide leading coefficients, and I have 1/2. Okay, and 1/2 is between 0 and infinity, and so by the limit comparison test, since the summation of 1/n² converges, so does summation of n+1/2n³ plus n. And then we've got that, right? So keep in mind your conclusions on these things are always in that sort of form of because we know this, we know that. That's a very math thing to have to do. But again, that just formalized the notion that the difference in degree is what's really important. And so anything along those lines, square roots and so forth, you can kind of apply them the same way. Okay. So let's look at one that's an exceptional case. I think I mentioned to you previously, I had a teacher once who didn't do the hard examples. So I tried to do some of the ones that are hard for us. Okay. So the example we're going to do, I guess I should share my screen first. And the one we're going to do here is summation n equals, you'll have to go from 2 to infinity, 1/n log n. So the reason that has to go from 2 to infinity is when you plug in n equals 1 to log n, you're going to get 0, and we can't have a division by 0 error. So again, our question is to determine convergence. So when we look at this, it's not really obvious what to compare with. So we might try to compare with just 1/n. That is actually probably our best comparison. If we tried 1/log n, that's another option that seems like might work here. But this diverges by p-series. So we're comparing it to something that diverges, okay? And so now we're going to take a limit as n goes to infinity and have the 1/n log n divided by 1/n, which would be the limit as n goes to infinity of n/n log n. The n's cancel. And now we've got a limit as n goes to infinity of 1/log n, which will be 0, okay? And so we say, oh crap, it's not positive, so we are in one of the exceptional cases. And so you'll have to maybe look back in your notes. For me, I have to kind of scroll back, and we'll look at if our limit is 0. If our limit is 0, and we had the thing we were dividing by diverge, well, that's unfortunate because the bn's are what we are dividing by, and those converged for the thing that gave us information. Crap, okay? So that means that the limit comparison test in the case of having L equals 0 didn't help us. And if we went back and switched and used, pardon me, used the 1/n as the top instead of the bottom, then we would just reverse things and it still wouldn't give us any information. So this particular case, the limit comparison test is not helpful. However, it does happen to be one that the integral test works for. And so try the integral test. And in particular, you'll have to think about the integral from 2 to infinity of 1 over x log x dx, which you can do a u substitution on that, and what you'll get is the limit as, let's say a goes to infinity of the log of a minus the log of 2, okay? And that's going to turn out to be infinity. So you can actually use the integral test to show that this particular series diverges, but the limit comparison test is not very useful for it, okay? So I wanted to make sure and show you an example like that where the limit comparison test just wasn't useful. But I don't want you to get the impression that every time that it doesn't work like that, you just give up, okay? So that's why we went ahead and looked at the integral test as something to help out on it. But I didn't work out all of the details because the integral test was something from a couple of days ago. All right. So let me take a look at another one that's kind of along these lines where it's in the exceptional case, but that maybe, and I told it to chat instead of share screen. So, but maybe something where it's still pretty hard to put all the pieces together. So this one here, we're going to do a summation equals 1 to infinity n squared divided by 3 to the n, okay? So looking at that, you can't use p-series stuff on it because 3 to the n is clearly not a polynomial. So you have to figure out something else to compare it to. The trick on this is that 1 over 3 to the n, the 3 to the n that's downstairs there, down the denominator, is way more powerful than the n squared. So it's going to infinity way faster. It's going to infinity in the nature of an exponential. So if you're asked on this one to determine convergence, then you want to compare it to something that is like the divide by 3 to the n. So I'm going to in particular think about 1 over 2 to the n, or 1/2 to the n. That is converging, and that's because it is a geometric series with the r equal to 1/2, okay? Remembering with geometric series, if the r value has an absolute value between -1 and 1, not inclusive, then you'll have something that converges. So now we're going to do taking a limit as n goes to infinity. I've got an n squared over 3 to the n on top, and I'll have a 1 over 2 to the n on the bottom, which is the same as the limit as n goes to infinity of n squared, and it'll turn into 2/3 to the n, okay? And if you spot immediately that, boom, that has to go to 0, that's great. If you don't, you might have to take the limit as n goes to infinity. Okay. My handwriting went to hell for a second there. So n squared over 3/2 to the n. What I just did there was to set it up to do L'Hopital's rule really easily. And so for L'Hopital's rule, you remember that you take the derivative at the top and the derivative at the bottom. And so the top, you'd have 2n And the bottoms, you'd have this 3/2 to the n times the log of 3/2. And then that's still infinity over infinity. So you'll do it again, and you'll have a top that is just 2, and a bottom that is still 3/2 to the n, and now times the log of 3/2, but squared. And now you have a denominator that's going to infinity and a numerator that's bounded. So you end up getting 0 out of it. At which point you say, oh no, it's that damned setup that we had before with the limit being 0. So scroll back up here, right? But now the thing that we're dividing by is actually something that converges, right? So since we were dividing by something that converged and we got 0, then that means that the rate of growth of the stuff that's in the numerator has to end up being slower than the rate of growth of the thing in the denominator. So by the limit comparison test, summation n equals 1 to infinity, n squared over 3 to the n converges as well. Okay. So that gives you a couple of examples here. Limit comparison test a lot of times formalizes something that you'll see intuitively, but other times it's hard to just spot what to get a comparison to, you know? And the question on your mind is, how do I know what to compare to? And mostly it comes from trying a bunch of things. The things where you compare to a p-series, pretty easy to spot. The things where the top and the bottom of your fraction are different types of functions. One of them is a polynomial and one is exponential. Usually you're trying to compare them with the thing with the higher growth rate. That's kind of where you're headed towards on it. If you get something that's thoroughly mixed, you know, like if I had a 2 to the n in the numerator and other stuff, and then a 4 to the n in the denominator, I would do the p-series type thing of looking at the higher growth rates, the 2 to the n and the 4 to the n, and think about, if I just divided those, I'd have 1/2 to the n, and that would be the thing that you would end up having to compare to. But more than anything, it's try a bunch of them for examples, and you eventually build an intuition. Eventually. And so, all right, y'all, go try some of these and build that intuition. And I'll see you in class.